Hello there and welcome back. We are starting a new and exciting chapter. And you're like, you always say that, Professor Clements. That's because I actually think this stuff is exciting. And we're going to be talking about batteries, right? The most important thing in the world to most people nowadays is my cell phone charged? And so in order to do that, right, you need a battery. In fact, you need a battery not only to run forward and drain and run your phone and do all those things that phones do, but you also need it to go backwards, which is to charge. So we have to be able to run a reaction forward, we have to be able to run a reaction backwards, and all of that is in the realm of electrochemistry. Oxidation reduction reactions, if you remember those from your introductory or your general chemistry class. So we're going to talk about all sorts of different things. Obviously, we have to start at the basics, the fundamentals of it. How do we write a good chemical reaction for these? We're going to balance chemical reactions. We're going to look at what are called galvanic cells. Galvanic cells are ones where we're going to generate electricity. We're going to run our battery and make our phone do things for us. How do we measure that potential? How is the potential related to energy that we have available? Remember, we talked in the last chapter about how delta G is a measure of the free energy, the energy available to do useful stuff. And so we're going to relate cell potentials, the energy you get from a battery, back to delta G and say, hey, that's the amount of useful energy we can get out of this thing. And then, just for fun, we're going to see how much energy is in a battery. And we're going to take a battery where we're just using about half a gram. And half a gram of iron, it's a big pinch of iron shavings in your hand. And we're going to say, how high could you launch a potato if you used all the energy that was available in that half gram of iron? We're going to talk about relating those potentials back to equilibrium constants. We related delta G to equilibrium constants, which means we can relate this back to equilibrium constants. Concentration effects. What happens when we're at non-standard conditions? Like say, instead of being 1 molar, we're 0.5 molar, 0.01 molar, 10 to the minus fifth molar. What happens to our cell as we do those kind of things? And we talk a little bit about battery technology. That's going to be at the very end. How do all of these things we just learned apply to actual batteries in the world, like the battery in your cell phone? And then we'd also talk a little bit about electrolysis. Electrolysis is the art of making the world go backwards. It's saying, hey, we use our battery to run our phone, but then we need to plug it in and charge it. How does that work? How do we make a reaction that wants to go forward go backwards? And then corrosion. Just like when you have weeds, right? Weeds in your gardens. All the definition in my world of a weed is a plant I don't want growing, right? It could be a plant that somebody else would want to grow, and for them it wouldn't be a weed. But for me, it's a plant I don't want growing. Corrosion is the same thing. It's oxidation reduction reactions that we don't want. Okay? So we're going to talk about those, kind of some ways of preventing those and such like that. But the first thing we have to know is our oxidation states. You did these in your intro chem, your general chem, so hopefully you have a good handle on these. How do we figure out the oxidation states? Now, in most cases, we're trying to figure out oxidation states of metals, because those are the ones doing most of our redox stuff, but there's cases when we're going to find oxidation states maybe of other things as well. But let's start with the metals. MnO4 minus. How do we do it? You remember, there's some general rules. Fluorine's always -1. Oxygen is almost always -2. Hydrogen is almost always +1. You go from those, and then you see where you go from there. So O4, right, that's a total of -8. And we're going to have to add whatever manganese is to that. And whenever you add all of your oxidation states, you get the total charge. And so I've got -8. Whatever place manganese is gets me to -1. So manganese in this case must be +7 in order for that to work out. So the oxidation state of manganese in that one is +7. For ones where you've got something like the lead and when the sulfate here, if I said the name of it, I'd give away the answer. Here, you know sulfate. It's a common ion that you're familiar with, and you go, oh, I know that sulfate is -2. It's one of my common ions. In order to balance out, -2 has to balance out with a +2, and so I've got lead +2 in this case. Here we've got oxygen. We've got -2. Now, notice we've got 2 oxygens, but generally people, when they're writing these things down, they're just going to write down the charge, the oxidation state of one of the things. So even though I've got 2 oxygens, each one is -2, so I write a -2 down. However, that's a total of -4. And right, if I wanted to write it out, I could say Ti plus -4 is equal to 0. Why 0? Because there's no charge on the overall complex, and so I got to add up to 0. So in this case, titanium is going to be +4. S8, all by itself, just sitting there. Right? What are oxidation states? It's when you've given away a charge or you've taken a charge. If it's just sitting there all by itself, does it have anyone to give a charge to? No. Does it have anyone to take a charge from? No. If you can't give a charge or take a charge, what's your charge? 0. Okay, so elements in their standard state. So if you just got a chunk of aluminum sitting there, that's going to have a charge oxidation state of 0. If you've got nitrogen, N2, that's going to have an oxidation state of 0. Elements in their standard state. Here's one you're like, I don't know what to do with this one. I've never seen this one before in my life. What are you talking about? Palladium and carbon monoxide. And this is one of those cases where you have to look at it and be like, okay, carbon monoxide. I've seen carbon monoxide before. I've never seen a charge on carbon monoxide before. So let me think about what would it be if that was a 0. Okay, and then what would palladium have to be in order for the whole thing to be a +2? You get a +2 charge on palladium, and that's not unreasonable. Okay, those are a little harder because you do have to be like, wait, can uncharged things go on? But we did. We saw when we were doing the complex ion formation, we saw plenty of things that complexed with ammonia, right? Ammonia, NH3 is uncharged, and that's perfectly fine. The complex ions, the complexes, they can form all sorts of things. So oxidation states, we know how to find them. The next thing we have to understand is that just because we see a reaction that looks balanced, it might not actually be balanced. So we're going to deal with these elements that you just deal with on a daily basis, I'm sure. And we're going to have some cerium +4 and some tin +2, both in the aqueous phase. And you'll find that a lot of what we do in this chapter is in the aqueous phase because it's really easy to make batteries in the aqueous phase. You can make them other ways, and we'll talk about that towards the end of class. But most of what we do today is going to be aqueous phase with maybe a solid present a little bit here and there. And so I'm going to draw a reaction arrow there. I'm just going to tell you that this turns into cerium 3+ and tin 4+. So you might look at that reaction. Okay, is that reaction balanced? And if you do regular old mass balance, which is what you've learned up till now most likely, you'd be like, well, I've got one cerium, one tin, all good to go. But you're not all good to go here, because not only do we actually have to balance atoms, right, which is the cerium and the tin, we also have to balance electrons. Do we have the same number of electrons on the left and electrons on the right? Now, looking at this and being like, do I have to count all the electrons in cerium and tin? No, you don't. What you can do is a quick way of checking whether your electrons are balanced is check whether the total charge is balanced on either side. So the total charge I have here is +4 +2 for a total of +6. And here my total charge is +3 +4 for a total charge of +7. That tells me that I am not balanced, that this reaction is not balanced. And I'm going to have to balance it in order to move on with my life. Okay, so that's just a quick way of checking. And what we're going to do next is we're going to say, how do we actually balance this reaction? How do we figure out how to make sure that we actually do have the same number of electrons on both sides? And I started with a really simple example. And as part of this example, I'm going to give you all sorts of rules that don't apply to this example. And you're like, why are you doing that? Because I want to keep the first example simple, but I also want to give you all the rules. And then we'll do another couple examples where I'm applying each one of those rules so you'll see it again. All right, so how to balance redox reactions. And if you go on the internet, you'll find people doing it slightly differently. Everybody's got their own little kind of trick and tip on this one. I like my way because, otherwise I'd do it a different way. But, if you're doing it other ways, as long as you're doing it thoroughly, you're not trying to guess. Guessing, not okay. You want to do this in a very structured, regular kind of way. And that's what we're going to try to do in this one. All right. So how do we balance redox reactions? The first thing we're going to do, the first thing you have to do is break the reaction down into two what we call half reactions. What is a half reaction? How do you have a half reaction? Well, a half reaction is either just an oxidation or just a reduction. And we call them half reactions because oxidation and reduction always have to occur together, right? If oxidation is the giving away of electrons, somebody's got to take them, right? There always has to be an oxidation step of giving, a reduction step of taking. But we're going to separate them out and pretend they're happening separately in order to do our balancing work here. So how do you break things down into two half reactions? Well, there's a lot of different ways, but essentially you have to identify what things are changing charge and then put them in their own reaction. So here it's pretty darn easy to figure out what's changing charge because everything has a charge. We don't even need to figure out oxidation states. Cerium is going from +4 to +3. Tin is going from +2 to +4. And so those are our two half reactions. We're not going to ever make a half reaction where it's cerium on one side and tin on the other. That wouldn't make sense, right? Because we're not alchemists. We can't convert cerium to tin. But we will see cases where we've got oxygen that's not there on one side, hydrogen that's not there on one side. Those will come as part of balancing. But the main element, the element that's actually undergoing oxidation or reduction, you need to have one of those at least on either side to start with so that you can do the balancing later. All right, so I'm going to write my two half reactions. I've got cerium 4+ going to cerium 3+. And you'll notice that as I'm writing this part, I'm going to be shall we say, not caring at all about writing phases or anything like that. However, when I do it all and put it all together at the end, I'm going to write a nice balanced chemical reaction with phases. And then the other thing that's happening is that I've got my tin 2+ turning into tin 4+. Those are my two things that I have going on. All right. So then what you're going to do, and again, a lot of these don't apply to this one. Step 2 is you're going to balance all atoms other than hydrogen and oxygen. So let's say on the right-hand side I had a cerium and it was Ce2SO4 or whatever. Okay, I would need to balance those two ceriums, so I'd put a 2 on the left to have 2 ceriums on the left and 2 ceriums on the right. I don't have that in this case, so I'm going to skip on to the next step. The next step is to balance oxygen using water. So let's say I had an oxygen on the right-hand side, a cerium oxide or something like that. What I do on the left-hand side is I'd add some waters, enough just to balance the oxygens that are on the other side. As I said, we will see examples very shortly of ones that contain these ones, so don't worry if they don't make sense right now. Hopefully after the example, they will make sense. 4, we're going to balance hydrogen using H+. Now again, we don't have any hydrogens in this one, but that's what we would do. We'd balance hydrogens using H+, right? We added some waters, so we know there's going to be some hydrogens there, and we're going to balance those or other ones that are already in the system using H+. Step 5 does apply to us. We're going to balance total charge with the electrons. Okay? Balance total charge with electrons. What do I mean by total charge? I mean what I did up here was I just took the total charge. I added up literally just the charge on this, the charge on that, not the oxidation states. In this case, they're the same. But let's say we had lead 2 oxide. It was PbO, right? In that case, they would have a charge of 0 because lead 2 oxide has a charge of 0. Even though the lead has an oxidation state of +2, I'm literally just like straight on just looking at the charges, looking at those superscripts, not looking at here's this oxidation state, that oxidation state. So it's actually easier than it looks. Now, in this case, it's going to be pretty darn easy. I've got a 4+ on the left. I've got a 3+ on the right. If I'm going to balance my charges with electrons, I'm always going to add it to the more positive side. Why? Because electrons are negative. Electrons will reduce the overall charge. If I put an electron over here, that wouldn't do so good because now I'd have +3 ± -1 is a +2, and I'd be getting further away from the charge on the left. So what I'm going to do is I'm going to put an electron over here. And I just need 1, right? Because now I've got a -1 + 4, let's say +3, is equal to +3. Cool, I'm balanced charge on that first reaction. And we do each half reaction separately. You don't try to like do the cerium and the tin at the same time, be like, well, I know I'm going to add 7 oxygens over here, so I need to. No. Just treat each half reaction completely separately from one another. Tin, you got 2+ on the left, you got 4+ on the right. How are you going to balance that out? By adding some negatives. You need a couple negatives, so I'm going to write E there, but then I'm going to put a 2 in front of it. So now I've got 2 electrons on the right of that one. And I've got +2 on the left, just from that tin +2. On the right, I've got +4 + 2 times -1, and that is +2. Okay, so I've now balanced out the charge on either side. The last, well, not really the last step. The last step of sorts is to balance electrons by multiplying reactions. Okay. What do I mean by that? Well, I said that one of the things we figured out at the beginning is even though our mass was balanced, cerium was balanced with cerium, tin was balanced with tin, we had more electrons on one side than we did on the other. We didn't figure out how many or whatever, it doesn't really matter. The nice thing about this method is even if you have no idea what's being oxidized, what's being reduced, or all that kind of stuff, if you follow the steps in a very methodical manner, you'll get it right. And then you can figure out, okay, what was being oxidized, what was being reduced. It totally works. All right, but anyway, we said, oh, look, we were misbalancing our electrons, and that's why our reaction wasn't balanced. So this last step here of the multiplying and adding things is balance the electrons. And what we want to make sure is that if cerium is only giving away a 1 electron, but tin expects 2 electrons, that's not balanced. And so what do we have to do? If tin is saying, I need 2 electrons, cerium says, I got 1, here, have my electron. Okay, I'm partially happy, but I'm not completely happy. So what do I have to do? I'm out of hands. I don't want to bring out my toes. But I need to bring in a second cerium. Yeah! I need to bring a second cerium in so that this cerium went to market. This cerium donates 1 electron. Bing! And this cerium, which is a different cerium, they're not like, paired even though they're on the same hander, boom, gives that second electron over to tin. And actually, it's the other way around now that I look at it. All right, tin is actually the one giving away electrons. Cerium is taking electrons. So tin says, I got 2 electrons, poof, puts them out into the universe. 2 things need to take those electrons, or 1 thing needs to take 2 electrons. That's how it's got to work. It's got to be balanced. You can't just have electrons floating around. When you get your balanced reaction at the end of this, if you ever find in your balanced reaction you've got an electron somewhere around, you missed a step and you need to go back and check your work. All right, so what do we have to do? Well, in order to do this, right, we need to make sure that this guy is balanced. Tin is giving away 2 electrons, so I need to multiply everything in this one by 2, not just the electrons. I can't just say 2 electrons. Notice I've got the parentheses there. 2 of everything. I need 2 ceriums, each of which are accepting an electron to accept the 2 electrons from the tin. Then the last thing you're going to do is add together, add your half reactions, and cancel. So in this case, we don't have other things to cancel other than our electrons, but sometimes you'll have water to cancel, you'll have H plus to cancel, and things like that. We'll see examples of that moving forward. So I'm going to add my 2 reactions here. What I do when I'm doing this is I just write everything on the left from the first reaction. Then I write everything on the left from the second reaction. Then I write everything on the right from the first reaction, everything on the right from the second reaction. I don't try to like bounce back and forth to try to figure it out, because I know for me, if I do that, I'm going to skip a term. Okay, so I literally just go through left to right. I've got 2 electrons. I've got 2 cerium 4 pluses. And then I'm done with that. There's nothing else on the left-hand side of the first reaction, so I go to the second one. I've just got 1 tin, right? I didn't multiply tin by 2. I just multiplied cerium by 2, right? So then we do that. On the right-hand side, I have to remember to multiply by 2. Some people like to put the 2's all the way through. I'm okay personally if I just put the 2 in parentheses. I usually do good with that. But if you want to put the 2 all the way through, by all means, go for it. Okay, 2 Ce3 plus, and then I'm done with that one, so I move on to tin and 2 electrons. As I said, what you will always 100% find is that your electrons will balance out. If you have 2 electrons on the left, you better darn well have 2 electrons on the right. If you didn't, you did something wrong. Okay, let's go ahead and cancel those electrons because they appear on the left, they appear on the right. That's the only thing that cancels in this case. So what do we end up with? We end up with a reaction that looks like this. 2Ce4 plus, and like I said, we're going to be fastidious about putting our phases in at the end. You're going to be very fastidious about that. All right, you're going to make sure to do that. Why? Because you need to. It's really important. The phases in electrochemistry are extremely important. And so you need to have all those in there. And we're going to go to 2Ce3 plus AQ plus SN4 plus AQ. And there we now have a balanced electrochemical reaction. Now, I'm guessing some of you looked at that run at the beginning, you're like, yeah, I think if you just multiply the cerium by 2, you'd be done. And you would have been right, absolutely. But I want to know that you know how to do this methodically, because some of them, most of them maybe even, are not so obvious that you can just like, duh. Right? So we'll see examples, and hopefully those will make you think, yeah, maybe this is a little harder than me just guessing. So there's your rules. You want to have those. You want to know those. Write those down somewhere. Study them so that you can know how to do them in order. If you try to balance hydrogen before you balance oxygen, you're going to mess up. If you try to balance electrons before you've balanced hydrogens, you're going to mess up. It's got to be in order. All right. So first check, let's just see, is this reaction balanced? We've got 3 aluminums, 3 oxygens, making 3 aluminums and 6 oxygens, and the answer is yes, no, or maybe so. Okay, what did you come up with? Well, hopefully you looked at mass balance. We've got 3 aluminums and 3 aluminums, we're good. We've got 6 oxygens and 6 oxygens, we are good. Then you looked at charge balance. You got a total of 0 on the left, and hopefully that's equal to 3 times 3 plus 6 times minus 2, right? Is it? We've got 9 plus minus 12 is minus 3. 0 is not equal to minus 3, at least not in my world, so this reaction is not balanced. Now, could we go through and do the... We totally could balance this chemical reaction. We're not going to, because we're going to do some other examples. But you know, if you feel like practicing, go for it. And by the way, the only way you can figure out this kind of stuff is to practice. All right, now let's go kind of stretch back in your mind a little bit to Chem 50, your first semester general chemistry class. You learned about oxidation, reduction, oxidizing agent, reducing agent. Remember, oxidizing, the thing that loses electrons. Reduction, the thing that gains electrons. Oil rig, right? Oxidation is loss of electrons. Reduction is gain of electrons. The thing that's oxidized increases its charge, more positive. The thing that's reduced decreases its charge. It's reduced. Right? More negative. So that's how we figure these things out, is oxidation reduction. The oxidation agent and reducing agent, remember, they're cross pairs. Right? The thing that's oxidized, because it's oxidized, it loses electrons. It allows something to get reduced, right? It's giving away those electrons, which allows the other thing to be reduced. So the thing that's oxidized is the reducing agent, and the thing that's reduced is the oxidizing agent. It's very convoluted language, but people use it, and so we need to know it. All right, consider the following balanced redox reaction. I'm telling you it's balanced. Copper 2 oxide and ammonia reacting to make nitrogen, water, and solid copper. Which of the following statements is true? You have copper 2 oxide being the oxidizing agent, and copper is reduced. You can read all those. I'm not going to read them for you, but you just have to try to apply those rules we just learned, those definitions, things you learned also, hopefully last semester or whenever you took intro or general chem for the first semester, and go. So what did we come up with? Well, it turns out, right, as soon as we find what's oxidized, then we know that something else is reduced, right? These things are always pretty well balanced. So we have to look at copper first, oxidation states. Copper's oxidation state plus 2. Why? Because it's paired with the oxygen. Minus 2 plus something is 0, plus 2. Copper solid, sitting there all by itself doing nothing. It's got to have an oxidation state of 0. Plus 2 going to 0. How are we going to do that? We're going to add 2 electrons. Right? If we add 2 electrons, that thing is being reduced, right? Plus 2 down to 0, it is being reduced. So copper 2 oxide is being reduced. Now, it looks funny here, and if you had different instructors who talked about it differently, you might have been confused by this one. I totally get that. Copper is the thing that's changing its oxidation state. It's going from plus 2 to 0. Even though at the beginning it's in this compound called copper 2 oxide, I prefer, and this is just my preference, it's not right or wrong, I prefer saying that copper was oxidized or copper was reduced. Some people will say copper 2 oxide was oxidized or copper 2 oxide was reduced. When we're talking about oxidation and reduction, it's always reactants. It's never, ever, 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 ever products. Right? So when we're talking about oxidation and reduction, we're only looking at these. We're never looking at those. Okay? So if I'm saying that copper is oxidized or copper is reduced, I'm really talking about the copper inside the copper 2 oxide. We decided that was reduced, so we know it's going to be either A or C, D. It's not going to be B or C. So if it's reduced, does that make it the oxidizing agent or the reducing agent? Remember, they always come in pairs. So if you're reduced, You allow something to be oxidized, and so you are the oxidizing agent, and so we get A there as our answer. Copper 2 oxide is the oxidizing agent, and copper is reduced. Funny, because one I talked about copper 2 oxide, one I talked about copper. I kind of did that on purpose because there's a lot of complexity to the language here. And you just have to be aware of that people can talk about the whole thing or they can talk about parts of it, and sometimes they'll use both in the same sentence. But as long as we know what's oxidized and what's reduced, we can kind of figure out the language as we go. All right, which of the following is not a redox reaction? So you're trying to figure out which one of those is not redox, right? There's nobody changing oxidation state. And go! Okay, let's go through them. Aluminum, what's its charge there? Well, you're like, I don't know. Well, hydroxide's a -1. You got 4 of them. That's a total of -4. You need to add up to you can do the math. You get aluminum is +3. Aluminum is +3. Already, if you've got a metal that's not changing oxidation state, that's a pretty strong sign that you might not have a redox reaction. But anyways, let's look around at everybody else. H. Here it's a +1. In water, it's also a +1. Oxygen, we could figure it out. It's a -2 there. It's a -2 there. If I'm down to oxygen, right? If I'm only down to one element, I've eliminated the other elements as they're not changing oxidation state. Oxygen can't possibly, even if you don't know how to do it, because whenever there's oxidation, there's also reduction. There's always going to be two things changing at least, because one oxidizes, one reduces. All right, how about the next one? C6H12O6 plus O2 goes to CO2 plus H2O. Whew. How are you going to figure that one out? Okay. Start with the easy one. O2, we know it's 0. It's an element in its standard state. In H2O, we know that it is -2. There we go. We've just figured out that oxygen went from 0 to -2. That is a redox reaction. Bing. Okay. Right now, A is a pretty strong contender. Okay, sodium, iron, chloride. Whoa, look at all these things in here. How are we going to determine? I mean, that's a complicated one. How do we know which one's the charged and the chloride and the sodium? Ugh. We're just being asked to identify redox, not redox. So as soon as we find one thing that changes, we know it's a redox reaction, even if we don't know what else changes. So let's look at the easy ones. Sodium liquid, what's its oxidation state? 0. And it goes to sodium chloride, what's its oxidation state? +1 in that ionic compound. So that is a redox reaction because we know that sodium was oxidized. H2O2 goes to 2H2O and O2. H2O2 is a funny one. Remember, we said oxygen is almost always -2. But if we did that, this would have to be a -4 total there, right? Which means my hydrogens would have to be +4, but, well, I only got 2 of them, and hydrogen only has 1 electron. So the max I can get out of that one is +2. So H2O2, the oxygen is actually -1, not -2. There's 2 of them for a total of -2, but each oxygen is only -1. However, on the right, what do we have? We've got an oxygen that's 0, and we have an oxygen that's -2. So this oxygen goes from being -1 on the left to -2 and to 0 on the right. This has a special name, which we'll talk a little bit more about later. Oops, disproportionation. Disproportionation reaction. It helps if I actually get that guy to look like an A. Disproportionation. It's a reaction where the same element is both oxidized and reduced. Okay, it's a disproportionation reaction, but it is definitely redox. CO2 plus H2 goes to CO2 plus H2O. Again, let's look at the easy one. H2, it's got to be 0. H2O, it's +1. We know that it's being oxidized, so that is a redox. And that first one that we thought about was our not a redox reaction. All right, that's the end of our intro to balancing chemical reactions. We're going to get to practice more in just a moment, so don't worry. The next video is more practice. We're not done with the practice yet. So now we know how to identify oxidation states, identify redox reactions, talk a little bit about the language involved in those things. Thanks so much for listening. Have a wonderful day. I just need to find my cursor now. There it is.